Okay, we're going to finish up chapter one, talking about thermodynamics. Here's the key concepts that we need to talk about. Again, most of this is a review from Gen Chem and organic chemistry, so we're going to kind of fly through it. If you have questions, I would suggest you go back and look through your Gen Chem book, your OChem book, and we'll just hit the high points. We're going to avoid the derivations of the formulas and talk about how they're used. So one of the key things for all the universe is energy must be conserved, but it can take different forms. So energy is neither created nor destroyed, but we can convert it from one form to another, from electrical to heat to mechanical motion to light. So in most biochemical systems, enthalpy is equivalent to heat. So we'll talk about enthalpy and entropy. And so enthalpy will be equivalent to heat. And we'll also talk about entropy, which a very simplified view is it's a measure of a system's disorder. And so a system tends to increase in disorder. But ultimately, it's going to be the free energy that determines if a process is spontaneous or not. And that depends on both the enthalpy, delta H, and the change in entropy, delta S. And so a spontaneous process occurs with a decrease in free energy, meaning the delta G will be negative. So we can calculate the free energy change if we have the temperature and the concentrations, and we know the stoichiometry of the reactants and products. Something a little bit different in biochemistry is we're going to define the standard state at a temperature of 25 degrees and a pressure of 1 atmosphere and a pH of 7. An important take-home message that we'll learn is that organisms are at non-equilibrium. So we don't want to be at equilibrium. That is what's referred to as death. So they say old chemists don't die, they just reach equilibrium. So we're going to be at a steady state, but it's going to be far from equilibrium. Meaning that we're going to take advantage of Le Chatelier's principle to push along reactions. We don't want to be at equilibrium where the products and reactants have come to level out, because then, again, we're dead. And we'll briefly talk about enzymes and how they increase the rates of reactions. So again, this is more introduction. We're going to hit most of these terms and concepts later on as we get more in depth and talk about enzymes. So this, I really can't stress enough that this is just really an introduction and overview. Make sure that you know the terminology and the vocabulary. And this is really just a presentation of tools that we'll use. So not a whole lot of concrete information being provided so far. A review and kind of an overview of tools that we'll use in the future. So just as a quick summary of what we've seen before, when we talk about thermodynamics, we talk about enthalpy, which is somewhat equivalent to Q. You can read in your book more about that it's not quite the same, but we can, for our purposes, say delta H and Q, or heat, are the same. And so enthalpy is the heat energy exchange between the reactions and its surrounding at constant pressure. And so we can classify a reaction that releases heat as exothermic, or one that causes the surrounding temperatures to decrease, meaning that the energy is being pulled from the surroundings into the system. And if you tested the temperature of the surroundings, you'd see that they decrease. And so in organic chemistry, we use these reaction coordinate diagrams to try to visualize the transformation from starting material to products. And so if the products are lower in energy, or there is heat released in the reaction, then we refer to that as an exothermic reaction. If we have to kind of push the reaction forward and put energy into it, and the delta H is higher for the products than the starting material, we refer to that as an endothermic reactions. So if we talk about entropy, this is the classical example that they use. So entropy must and enthalpy must both be considered when predicting whether a reaction will occur. And so delta S, like I said, we often talk about molecular disorder. It's a little bit more complex than that. It's actually about energy dispersal and freedom. So if we look at the system here where we've got two spheres connected by a valve, you can see that those molecules are confined into one sphere. And so if we open up that valve, what you see is that those molecules will move randomly, but they will occupy more volume. And so we would say that they are now more dispersed. And so their energy is now dispersed between the two spheres. They've gone from an area of high concentration to areas of low concentration. And so we say that the entropy of this has increased. But really it comes down to Gibbs free energy, which is the relationship between delta H and delta S. And so here is Gibbs free energy. And so it depends on the enthalpy and it depends on the entropy. Now you notice that the entropy term actually has temperature appended to it. And so that is how we can favor reactions. Generally for a reaction, delta H is going to be fixed because those are the bonds broken and the bonds formed. The entropy is going to be fixed because we're either going to get ordered or disordered, but we can play with the temperature. And so this term, when we look at the equation, this is the term that we can actually influence right here by altering the temperature. Otherwise, you'd have to change the reaction completely. But for any reaction, we can play with temperature to either get the reaction to go or not go. So Gibbs free energy is the one that takes into these two accounts, kind of the bonds broken, the bonds formed, and also the dispersal of the energy or the entropy. And you can see their definitions there. But in Gen Chem and OChem, you should have seen this where we can actually determine if a reaction is going to be spontaneous or not just simply by looking at the signs of delta H and delta S. And this is just simple algebra where if we take delta H and it's negative and we take positive delta S, so you notice again that we have this negative term right here, or we're subtracting the T delta S. So if we have a negative, subtract a positive, of course, overall, that would be negative. So this is in cases where delta H is exothermic. So enthalpically favored, we're releasing energy, and it is becoming more disordered. So delta G will always be negative. Now, in some cases, we can have where one of the terms is favorable and the other term is not. So again, a negative delta H is a favorable term, energy is being released, but a negative delta S means that the system is getting organized. Either we're going from 2 to 1 molecule, or in some way the system is becoming more organized. And so again, algebraically, if we take the negative here, times a negative delta S, what we see is this whole term right here goes positive. And so now we have a favorable delta H, but we have a positive term. And if the requirement for spontaneous reaction is that delta G is negative, then we want to keep this in blue. We want to keep it small. So we don't want that term to get too big. So if this term gets too big here, then the whole delta G will become positive. So if we want to keep this term small, then what we do is we keep the temperature low. And so what we can say is delta G is negative when, let's try that again. When the temperature is low. So delta G is negative when temperature is low. One way to remember this is when you have negative, negative, you want to keep the temperature not negative, but low. Okay, so let's do this exercise again. So in this case here, what we're going to find out is the delta H is unfavorable because it's positive, it's endothermic. So we've got to be putting energy into the system, but we do get disorganized. And so again, this whole term right here, since it's positive, and again, we have negative here, this whole term is going to go to a negative. So now we want the term in blue to win. And so if we want the term in blue to win, then what we're going to do is delta G will be negative. Again, we want the blue term to win. We want it to be as large as it can. So when the temperature is high, so if we times this by this delta S by T, and then we subtract it, we want to make this term as large as we can. And so we want a large temperature. So another way to remember that is positive, positive. The temperature needs to be positive or very big for the reaction to be spontaneous. Okay, and then finally we get to the very last one, and you can see algebraically there is no way for this to ever turn out to be a negative term. So again, this negative T times a negative delta S will always go to positive. So in this case here, delta G always positive. So in the end, we've got four different options. Delta G will always be negative, and that is when our terms are favorable. We're releasing energy and we're getting disorganized. We can make delta G negative if we have an unfavorable delta S by keeping the temperature low. We can make delta G negative if we have an unfavorable delta H by increasing the temperature. And down here, there's not much we can do to make this a spontaneous process, a negative delta G. Again, a non-spontaneous process doesn't mean that it won't occur, it just won't occur without external influence. It's just not one that is going to go without additional factors to get that reaction to proceed. So something that we need to talk about in thermodynamics is just the standard state. So not all reactions are run at the standard state, and in biochemistry, we modify those standard states. That's what that little degree symbol here, or not, stands for, is that we're looking at delta G in the standard state. And so STP, standard temperature and pressure, is 298 Kelvin. Standard pressure would be 1 atmosphere. Standard solute concentration would be 1 molar. So we actually change some of those. So in the biological, so now this is G naught prime, and this means that we're looking at standard conditions in a biological setting. And so the what we do is we look at a pH of 7, which means that the H plus concentration is just going to be 1 times 10 to the negative 7th instead of a 1 molar. So we're not going to really look at 1 molar concentrations. Those aren't really biologically significant. And then something that we won't, we'll talk a little bit about it in the next chapter, but the concentration of just pure water is 55 molar, which is a very high concentration, meaning that in 1 liter of water, there's 55 moles. And we're going to treat that activity of water as just 1. In other words, we're going to kind of ignore the concentration of water, because in biological systems, the water is really not going to change its concentration. The solutes will change concentration, But again, we're going to be working at very low concentrations like millimolar. And so the overall change in concentration of water is not going to really be significant. And so in essence, we just ignore the concentration of water and we don't worry about its concentration and its changes when we do these calculations. Okay, so a couple equations that you should know. So if we have a reaction up here, we can actually calculate the delta G of that reaction if we aren't at a standard state. So if we're at a different temperature here or we're at different concentrations, we just need to know the delta G naught prime. And so you can look these up in tables, and then we can take the gas constant, we can take T, and we can take our new concentrations and calculate the delta G of the reaction in conditions other than those in the standard state. Now, there is an interesting thing about this reaction if it's at equilibrium. And so if a reaction is at equilibrium, then what we know about the delta G of the reaction is it's actually at 0. So it's neither so it's not spontaneous because the rate of the forward reaction is equal to the rate of the reverse reaction. And so delta G of reactions at equilibrium actually go to 0. So if we take the delta G of the reaction here, and we know that it's at equilibrium, then we can plug that in here. And what we end up with is a new equation. So if we actually know the equilibrium constant of a reaction, we can actually calculate the Gibbs free energy at the biological standard state. So like I said, you can look these up in tables, and we can, again, calculate those if we know the equilibrium constant here. Okay, but equilibrium actually depends on temperature, so we can actually look at the change in the equilibrium constant as we change the temperature here. And this is known as the Van't Hoff equation. Okay, let's kind of close this up. Here's some terms that you should know. So angstroms, that's typically the unit that we measure in biological systems. And so it is equal to 10 to the negative 10 meters. We'll talk about calories. Even though the SI unit is actually a joule, we'll use the big calorie, the big C, which is also what you find on the back of your food, which is referred to as a nutritional calorie, which is 1 kcal. When we do calculations with temperature, we need to make sure that we're using Kelvin, the absolute scale. We'll talk about numbers of things, and we use Avogadro's number, 6.022 times 10 to the 23rd, because atoms and molecules are very small. So we need some way to express a significant amount of molecules, and that just ends up being Avogadro's number, which we can also refer to as a mole. The gas constant, when we're calculating energy, is 8.31 joules per Kelvin mole. And then again, you should remember all your metric system prefixes. So what a micrometer is, a nanometer, centimeter, decimeter, kilometer, and all those good things that we've hashed before. So we'll leave you off in this chapter with kind of an overview of what we'll be talking about of, how does life work? So somehow we had to go from these very small molecules that were able to replicate. We were able to then put them into a membrane-bound compartment. That brought a lot of advantages because we could increase the concentrations inside that compartment. We could get the molecules and other machinery in close proximity, so that would speed up reactions. And that allows us to process molecules and get energy to do work. But as I said earlier, organisms live at a non-equilibrium state. So in all living systems, energy flow is exclusively downhill. We want that to be a spontaneous process. We want life to always be favorable. So in addition, nature is inherently dissipative, meaning that we're releasing energy to the environment. So as you're sitting there listening to this, you're releasing heat through your skin, through the top of your head, into the environment. And that's coming because you're doing metabolic processes and capturing that energy. And that energy isn't 100%, that energy capture is not 100% perfect, so we lose it as heat. That heat also serves a purpose. We use it to maintain our bodies at a constant temperature so that our reactions run at a expected rate. If we happen to be a cold-blooded animal, then when night came and it got cooler, our reactions would actually slow down. And so we would become less responsive. And so in order to become responsive, we need to expose ourselves to some solar radiation. And that's why snakes and lizards will go out on rocks and sun themselves to get their body temperature up to a up to a temperature where their metabolic processes can occur at a rate that they can actually become more responsive to their environment, meaning that they'll move quickly, be able to catch prey, and also escape predators. So again, chapter 1, really just kind of an overview of what we'll talk about. Chapter 2, we're going to get a lot more in depth into water because it plays such an important role in biochemical processes. And then finally in chapter 3 is what I would refer to as biochemistry, when we start talking about biological molecules and how they relate to a biological system. So we will have that up soon. And again, office hours, I'm going to be meeting Monday through Thursday from 8:30 to 10. So if you have questions, you want me to go over material, soon we'll have some worksheets and we can work on those together. So I will just be here waiting patiently for questions or just someone to come visit me in my loneliness.